Okay, I think we can get started now with the last talk of this workshop. And as I mentioned, we're going to cover one more type of kind of deep model referred to as a variational autoencoder, which is also defined kind of early on in like the 2013-14 range, and has a kind of wide range of applications, although it seems somewhat trivial at first. So I want to go through what exactly this autoencoder concept is. So an autoencoder is basically a tool, or at least in one application, a tool for extracting features in an automated way. As we mentioned at the beginning of the last talk, it's difficult in complex data sets to really determine what are the defining features, what actually characterizes that data. For digits, again, maybe we have symmetry, pixel intensity, we can come up with that, but handwritten digits are a very, very simple case. If we're looking at kind of highly complex data, how do we actually go about doing that? And ideally, we want that to be done in an automated fashion. So here I just kind of go through some terminology. This isn't kind of used by everyone, but what we're looking for are features that are completely characteristic or completely define the training examples that we're working with. And to be more precise, we want to kind of think of what does it mean to completely characterize something. And in a simple but natural way to define that would be a set of features characterizes this example completely if we can take those features and nothing else and reproduce the original data. So reproduce everything. Okay. So this is a kind of a natural way to think about characterization and a way to find the important features if we can somehow accomplish this. And it turns out that this really has a very natural or leads itself to a very natural approach for automatic feature extraction, which is to train a neural network to learn the identity map. We're going to give it an input, say x, and we want it to output x. Okay, so this is really easy, obviously. We could just use no layers and just have it output whatever it's been given. But the one caveat that we'll introduce is that we want to have a bottleneck or a kind of reduced dimension layer somewhere in our network so that it can't just take that input, pass it along unchanged, and give us our output. Instead, it has to compress or encode some information about that input, and then basically come up with a way to generate or decode that information which has been compressed back to the original data that we started with. So you can almost think about this as like an automated compression scheme. It's learning how to kind of compress and decompress the data from the kind of data set we're working with, and we can interpret that bottleneck layer of features as these defining characteristics, because that decoding, that decompression phase allows us to go from features to original data points. So the autoencoding model, in just kind of a very basic sense, starts out with something which is kind of large and structured here on the input. It has some number of hidden layers. It reaches a bottleneck, which we refer to as the encoded features, typically. So these are the kind of small dimensional features that we are hoping will uniquely characterize the output data, and then we build back up similar to a generative model. So we slowly build up through hidden layers until we get a reconstructed approximation to the original input. Okay, so we're still aiming to map the identity function, but by introducing this bottleneck, it has to do something more clever than just passing those values through. So this is a great idea, but we have to be able to train these effectively. Okay, so we can define, a really small bottleneck, but the network may not be able to learn a representation or a compression, decompression scheme, which is able to reproduce those values accurately. And so in the paper Autoencoding Variational VAEs, Kingma and Welling introduced a theoretical or a kind of probabilistically justified approach to this autoencoder for basically handling the autoencoding process as a latent variable model. Those encoded features are interpreted as unobserved variables or kind of parameters, which are used to generate that feature. So something almost like DNA, you can kind of think. It's something, I mean, we can observe it, but maybe we don't know what the specific values of our DNA are, but they correspond or they produce something, a person in particular, which has some kind of high-level features. But we want to get to the core with this autoencoding concept, or identify that latent information. We want some way of getting that, the kind of essence of the example or the characteristic features. So in order to do this, again, in kind of this Bayesian inference framework, what they proposed is to incorporate a sampling procedure at the latent level. So the encoding step now, or encoding features, are referred to as latent vectors or latent variables in some latent space. Okay, so we think of this as some space, some manifold, and we're going to inject noise to perform a sampling procedure and use this Bayesian inference framework to reproduce from that latent information the original input. So there's a kind of a stronger theoretical background in this approach, which helps training considerably. Just a TensorBoard model. Here I've used namescopes to kind of consolidate layers. But again, we take our inputs. We have an encoder. So this is going to basically generate something in the latent space or give us at least a location, some information about the latent space. We then sample based off of that information we've been provided and decode or generate an image or a prediction, some structured data, which is designed to replicate that input. Now, in order to do this, as I mentioned, we are sampling. So we have to make sure that that's compatible with backpropagation, that this is still a differentiable process, and that we have gradients connecting our weights all the way out to our prediction. So to do this, or to accommodate for this constraint, we introduce a random sample, epsilon in this case, which we will use to scale the predictions from our encoder. So our encoder will give us means as well as standard deviations. And if we want to sample a random normal in a location mu with standard deviations, so these are independent by construction, just for basically feasibility in the implementation. But these standard deviations are scaled by that noise vector, and this gives us the same output, the same result, as just sampling from a normal mean mu and diagonal covariance matrix with sigma along the diagonal normal distribution. Okay, so mu and sigma are still used here, but the randomness is contained in this epsilon. And the benefit of that is that for each training step, there's one sample, but this epsilon is fixed. So the dependency between, for instance, sigma and the outputs or mu and the outputs are still differentiable. They're going to be changing from one step to the next, but that's okay. We already have a stochastic optimization procedure. This will add a little bit more noise to that, but it's acceptable. And what we'll learn is effectively on average. We'll try to learn on average, and I should note it's important to use larger batch sizes for this reason as well. So we'll take a large number of samples and examples, and we'll take that noise and hopefully on average still achieve something, and it won't add too much to the noise. And in practice, this is not actually too much of a problem. One practical note that is important to take into consideration is, again, we're using logs here. So we actually don't want to predict the standard deviations for numerical stability. Instead, we can just predict the log of the standard deviations, and this has an extra benefit, which is that by predicting the log standard deviation, we can actually predict positive, negative, arbitrary values. It doesn't matter. So we can produce these with a network layer without an activation function, whereas the standard deviation would have to be predicted using a strictly positive value, which can be difficult to enforce on a layer. Though certainly is possible. But really this is for stability, and we can just apply this by applying the exponential function to this log sigma, which is the direct output of our layer, and then multiplying that by a random sample and adding it to our mean. So that's the implementation that we'll use, for example, in the GitHub code. So as I mentioned, there's a complete Bayesian framework behind this. I will not go into it in much detail, but I would highly recommend referring to that original paper if you're interested. That paper, as well as the GAN paper, have some very interesting interpretations of this kind of neural network architecture in terms of distributions and probability theory. The very basic, oversimplified idea behind the variational autoencoder is that we can think of a kind of two-component model, Bayesian model, in which we have a posterior which is intractable. So the true posterior, referring to the conditional distribution, what is the latent variable, provided that I know I'm working with this input data x. So I have some data x, and I want to know what's the distribution, what are the kind of the probabilities that I have a certain configuration in the latent space. And so you can write this out, but it turns out to be an integral, and we don't have basically one of the terms used to normalize it, so we can't actually compute this. So instead, what we could propose is to define an approximation, which they refer to as a recognition model, Q sub phi, which again is going to give us basically a distribution of the latent in the latent space, provided a specific input. And we're going to try to approximate this the best we can. And the parameters here, the theta and the phi, are relative in the sense that where we are in the latent space depends on how we decode. So these theta parameters are representative of the decoding component, the generative component. And so even the true distribution is going to depend on that. So that's why we have theta here even in the true, but those are the decoding parameters, and the variables phi are in the encoding or the recognition model. And the nice thing is that we can update these simultaneously, as they discuss in the paper. So this is really a very simple training process. We don't have to, as was the case in the generative adversarial network, separate our gradient computations. We can do everything at once, which is convenient at least. So again, the basic idea, we have a recognition model, and then the generative model is interpreted as the probability distribution of over x in your data space, provided a latent vector z. So again, now in this probability context, the encoder is a recognition. So it's saying I have some input, where in my latent space should that be, and sample from that distribution. There are many possibilities in this kind of variational inference setting. And then from that sample, generate a possible approximation to that original input. So very much similar, just justified with probability theory in the background. So the probability theory underlying this also requires this Kullback-Leibler divergence, but I just wanted to motivate kind of why heuristically it makes sense to use. And the understanding that I have, or kind of the intuition, is that when you're using these encoder-decoder models, it's helpful to anchor your position in the latent space. So for instance, it's kind of natural to assume that your encoded representations lie in some normal distribution. In particular, we'll assume that for variational autoencoders. But the mean and the covariance matrix can be quite arbitrary, and in particular, from a theoretical standpoint, there's no difference in the case where you center your distribution around 0, for instance, or you center it around some value 10, 0, 0. It doesn't matter where your center of this distribution is. Okay, you should still be able to process that without any problem. Your encoder and decoder just have to be on the same page. So if the encoder sends everything in a kind of a rough neighborhood of 10, and your decoder is aware of that, that's fine. And likewise, if it sends it near 0 and your decoder is aware of it, it's fine. There's no difference mathematically. The problem is that this ruins kind of the well-posed nature of the problem, because there's an infinite number of configurations in which the optimal performance can be reached. Okay, it could be at 0, it could be at 10, it could be anywhere. So there's this whole family of solutions. And in particular, this could be kind of slow in the learning process because it might kind of drift. It doesn't need to, but the gradient calculations may have kind of a flat line which follows this infinite family of solutions. And to avoid that, we can just say, okay, look, we would just like you for no reason other than that it can be anywhere, to stay near 0. Okay, so stay near 0 and keep your covariance roughly equal to the identity matrix. So let's just stick with a standard normal distribution, because there's really no reason why it shouldn't be that. We just need to give it an extra motivation to follow that distribution. So the Kullback-Leibler divergence is exactly a way of kind of enforcing this. It's kind of a directed measure of distance. So the KL divergence, as it's referred to, is going to be introduced into our loss function as a sort of a regularization term, or an anchor, as I referred to it previously. And what we want to do is take this standard normal that I had, as I mentioned on the previous page, so centered at 0 with an identity matrix for the covariance. And we want to take the directed KL divergence between that and our actual outputs, what we're actually getting, this mu and sigma from our encoder. And we're going to add this to our loss function in addition to what's referred to as the reconstruction loss. So again, this is coming from the underlying Bayesian framework. So these are the two components used for the expectation lower bound, or the elbow loss, or the negative elbow loss, which we will use to define our full loss function. So the reconstruction loss will correspond to how accurate our reconstructed version of the original data is. So like, does it look like the image that we provided it, for example? And the KL divergence term will anchor the position in the latent space. So we'll say, make sure you're close to 0 in terms of your mean, and that your variance is approximately 1 independently in each direction. So here's the calculation. To make this kind of tractable, or just convenient, really, we've assumed that we have a standard normal distribution produced by our encoder, and we're assuming that our target distribution is a standard normal, or a standard normal as well. And the benefit of this is that we can compute the KL divergence in closed form, especially if we make an additional assumption that these latent variables are independent. So this is kind of referred to as disentangled. So there's no relation between them. They're kind of distinct variables which control distinct aspects of the data. And that they are, or which implies rather, that we have a diagonal covariance. So we can actually compute this KL divergence, and it's a very easy formula to implement. It's just the variance plus the square of the mean minus 1 minus the log of the variance, and then you basically sum those up. So that's the KL divergence, which we can compute quite easily. And then the second term, in some cases, we have to make a stretch. If you're doing something like regression, you somewhat have to depart with the strict theory justifying the model. But in the case, for instance, of binary classification, in particular with a Bernoulli prior assumed, the reconstruction loss term, so here this expectation, is exactly the negative of the binary cross entropy, which is what we expect because we're going to have a negative sign anyway. So basically our loss automatically will include the binary cross entropy. So this is just the binary case of the softmax cross entropy that we went over earlier. So this is convenient. We can compute both of these, and they showed or demonstrated that this works quite well. So as I mentioned, there's this concept of latent space and kind of positioning in the latent space. As I mentioned, kind of we hope that we can force it to be centered around 0 roughly. But our actual data will be distributed in that region, in this normal region, in kind of interesting ways. And for example, one thing that we can do is to interrogate this latent space after we've trained the model by basically fixing some positions. So we can use our recognition model, our encoder, to take an input image of, say, a 3. We can figure out where that lies in the latent space. Okay, so we encode it to get a latent vector, say Z0, corresponding to an image of a 3, such as this one on the left. And we can also find a representation of, say, a 7. So the encoded representation of this 7 may be Z1. And we can ask ourselves, in this model's understanding of these handwritten digits, what lies between, at least in this linear sense, a 3 and a 7, or more specifically, this 3 and this 7. And we can actually start to see that space. So I've just done a linear interpolation here with a fixed number of steps, and we see the 3 somewhat blending, the bottom edge retracting, the middle edge flattening out until we get something of a 7. And so this is the connection, or the learned representation, within that latent space. And more generally, and this is taken from the original paper, Autoencoding Variational Bayes by Kingma and Welling, we can look at kind of the whole range to some extent of how these values are organized. And we see, again, that 7 is kind of close to a 1. There's a connection kind of between the 7 and the 4. The 3 and the 8, as we would expect, are somewhat close. And there's this organizational pattern that the model has automatically realized. It's automatically created for itself. Okay, and so this is the idea of this autoencoder. It basically takes our data. We have not told it that these values are 7s or these values are 8. It's just learned that on its own. So just to emphasize this or to show this, if we look at the code for the VAE, we're not using the MNIST data anymore. Instead, we're using the MNIST images file. So let me make sure this is the VAE. So find our parse function. So we're going to be parsing just the images. And we can still see this same approach. So we're just going to get the image back. But what's going to happen is it will learn that in our latent space, if our encodings are close together, then we're likely predicting something which is of the same class. So it almost naturally gives us this kind of clustering in the latent space of the digits. It can be used in a kind of sort of a classification sense. You can maybe use the encoder and take that out to define a classifier. And actually, I should have mentioned in the previous section, one of the additional applications in the generative model is that you can take the discriminator. As I mentioned, I use the same discriminator component as I used for the classifier. And it turns out that actually the discriminator makes a very good classifier. If you first train a generative model and you take that discriminator, you save it, and then retrain it with those weights in their final position from the adversarial training, it actually can improve the performance significantly if you then train those already preconditioned weights to the task of classification. So that was another kind of interesting point on the GAN side. as you can kind of see, there are a lot of different variations, and I just wanted to point out at least some references. I kind of like this site. It's basically updated fairly regularly with deep learning papers with importance basically ranked by citation counts. And it's a good way to at least filter through some of the papers because there are so many coming out. It's quite difficult to keep up with them all. But at least as you're getting started, you can really work your way up from these older papers with high citations, kind of understand the foundations, things like the Kingma paper and the Goodfellows paper that we've went over today, and then work your way up to the new research that's coming out. So I'll leave the code to you. As I mentioned, it's really almost identical to all of the other models that we've worked with. The only difference now is that we'll have a sampling procedure. If we look at that, the sampling procedure is quite simple. The only note is that, as we mentioned, we wanted to use that reparameterization trick, but that's very simple. We just define epsilon to be a random normal with the shape of our predicted log standard deviations, and we add the mean to the product of that epsilon noise vector with our exponential function applied to the log standard deviation, as I mentioned on that implementation slide. So that is all that I have. I will be around for the next half an hour or so. If anyone has any questions, more specific questions, wants to go over any code or anything, I would just like to thank you again for attending. And if you want to join the bi-weekly machine learning and deep learning group that we've set up, please talk to myself, Hongshan, or Dominic after today's workshop. Thanks.